The last thing we're going to talk about in this module is pH, which has to do with acids and bases. So while it's not a chemical reaction, it fits here very well for us. You are going to see, when you look at cosmetics, you are going to see things like pH balanced. And so the question, of course, is what does that mean and why is it important? So I want us to think about acids and bases for just a second. And I want us to look here at water. Water is a neutral solution. And what we mean by neutral solution is the amount of H3O plus and the amount of OH minus equal each other. Now, I want you to remember that I said, hey, look, if you're looking at OH minus here, that is the hallmark of a base. So if you've got OH minus, it screams base. If you've got H3O plus, it screams acid, right? And so when we look at these in solutions, you have both of them. And the relative amount of each one affects the pH that we see. So in a neutral solution, what you have is the amount of H plus equals the amount of OH minus. When you multiply these two together, it equals 1 times 10 to the negative 14th. Now, that's for us here in this class. If you were to go on in chemistry, you could see some differences in this based on things like temperature, but we are not worried about that. So this is what we have, and a neutral solution has a pH equal to 7. If you have a very basic solution, so for example, we have sodium hydroxide. We learned in the previous screencast that is a strong base, right? And it's a basic solution. And when we look at the ratio of the H3O plus to OH minus, or, remember, this is interchangeable for H plus, what we find is there's a lot more OH in the solution than H plus, right? Because these things are relative to each other. And so that translates into having a pH that's greater than 7. In acidic solutions, we have a lot more H3O plus, which is H plus here. So here's hydrochloric acid. And that translates to a pH that's less than 7. So these are our 3 pH values. So let's talk a little bit about what pH is and how we calculate it. So in the when we look at this, right, there's a few things that you need to note when we talk about pH. When we talk about the concentration of either the hydroxide or the hydronium ion, you are going to notice first off brackets. Brackets just mean the concentration of something. The other thing you're going to notice is an uppercase M. This is a unit of concentration. The name of it is molarity, right? And that's all we are really concerned with in this class, right? That's the unit that we're going to use with concentration. So when we're trying to figure out the pH of something, pH equals the negative log of the concentration of H3O plus, okay? So for example, if our H3O plus concentration was 5 times 10 to the negative 3, and that's molarity, or sometimes that's called molar. You'll hear it called molar a lot. What we would do is we would say, okay, to calculate the pH, we're going to take negative log, and we're going to put in 5 times 10 to the negative 3 molar. And when we do that math in the calculator, we should get 2.30. Okay, this pH is less than 7, so this solution is acidic. Okay, because these are a ratio, it's important to note down here that if you add the pH and a unit value called POH, that gives us 14. Well, what is POH? POH is just the negative log of the concentration of the hydroxide ion, right? And if you look here in the middle of this scale, you'll notice if the pH is 1, the pOH is 13. 1 plus 13 adds up to 14. If the pH is 2, the pOH is 12. 12 plus 2 adds to 14, okay? So you can see here the relationship between those. That's very helpful when solving problems. Few things to note here. When we look at things that are acidic, you have stomach acid, lemon juice, cola, vinegar, wine, tomatoes, black coffee, rain, if you talk about acid rain, saliva, those are all acidic. Things that tend to be basic are things like human blood. The pH of human blood is 7.35 to 7.45. Seawater, borax, this a lot of times is used in cleaning solutions. Lime water, this is not the fruit lime water. This is like slack lime or things that have ions in them. Ammonia and bleach. So all of these are quite basic. Well, let's now talk about the skin, okay? Because we're here in this class, we're interested in cosmetics, and skin has a pH, right? And the solutions of things that you put on your skin are also going to have a pH. Now, when I was putting together this information for you, and I was doing a lot of research on skin pH, I found everybody kind of agrees on this range that's kind of wild. It's like 4.5 all the way to 6.5, right? So I had a book that said it was 4.5 to 6.5. But when I started to look at more recent research, and so I have this article here that you can more than welcome to look up. We are seeing some kind of different numbers. And so, and you can see I grabbed this graphic. It's showing pH here from, right about a 4 to right under 6. And that's not quite correct. It's not correct. It just doesn't agree. So we're going to go with what this article says. Everybody can agree that skin pH is just naturally acidic. But your skin pH does have a range. And that depends on a lot of things. It depends on how much you sweat, your skin oils, as well as certain biomolecules. And so we're going to go with this article, which says pH is 4.5 to 5.8. So your skin has an acid mantle, right? And that acid mantle is kind of like a coating that makes your skin a little bit acidic. It's made of sweat, right? And skin oils like sebum that we talked about earlier, right? As well as some biomolecules. Things like cholesterol, ceramides, enzymes, all of those things are part of that acid mantle. Now, the reason this is important, it's super important for us because in an acidic environment, harmful bacteria will not grow. So the fact that our skin is acidic is it keeps this harmful bacteria from growing. And so a lot of times what you'll see is that it supports the skin's natural biome. So when we talk about microbiome, you have all sorts of things. We talked earlier, you are not alone, right? You're never alone. You always have little microbes that are living on your skin. And kind of this idea is you want good microbes, and you don't want bad microbes. And the skin pH helps keep the good microbes happy and discourages bad microbes from growing. So when we develop cosmetics, right, we don't want this to disrupt the skin pH. We can have some problems if it does. So if you have a product with a pH that is too high, right? So this would be something that is basic. A lot of times it's called alkaline. You hear the word alkaline used. It basically strips the skin's natural oils and disrupts that acid mantle. Now that to us leads to things like dryness and irritation, inflammation, sensitivity, increased water loss, eczema. Those are the things that you'll see there if you've got kind of this basic product that you use over and over that changes the pH of your skin. Now, that being said, you can also go too acidic, right? So products that are too acidic, right? They have that low pH, right? So, right, can also cause things like redness and irritation and chemical burns if the pH is extremely low. This is used a lot of times in acne medicine. Acne medicine has a lower pH, or like if you think about retinoic acid, right? That's got a lower pH. And that's why one of the side effects is that reddening of your skin. Now, cosmetic products are formulated to be pH balanced. Now, that does not mean that pH is at pH 7. That doesn't mean it's a neutral pH. It's going to mimic the skin's natural pH. So we're going to see, when we talk about pH balance, you're going to see products that are 4.5 to 5.8, right? That's that pH kind of that matches the skin. And that supports the acid mantle and really prevents these adverse reactions from happening. And that's particularly important for really sensitive skin or skin that may be compromised in some way or damaged. Skin research and this pH is still kind of this ongoing research. So I went to Google Scholar when I was looking for, which is a great website. It searches the scientific journals because I was just curious about cosmetic skincare products and the different pHs and how it affected the microbiome. And this is kind of a neat article. I just have kind of, this gives you kind of a rundown. The article itself has all the data and things like that, but this is just kind of a snapshot. And it talks about, the human skin acts as a protective barrier. The importance of pH for the microbiome is paramount. Cosmetic skincare products interact with the skin microbiome and skin pH, and they really play a key role in maintaining that microbial balance, which is important. Research suggests that products with non-physiological pH levels may disrupt the skin microbiota. Our clinical study aimed to evaluate the effects of low pH cosmetics, pH of less than 5 on the skin. Now, that is kind of interesting because we see some other references that give the pH of, that if your pH less than 5, depending on how less than 5, you may be in that pH range of the skin. And so it looked at the skin microdiversity for 28 days of 4 different low pH cosmetic products. So vitamin C, resveratrol, a collagen mask, and then a native algae mask, right? And they looked at the forearms of postmenopausal women with a skin pH of greater than 5.5. So that is how, right, they're controlling for the variation in the skin pH on this study. They're saying we're only going to look at people with a pH of skin that is greater than 5.5. So if we have a pH of that's less than 5, which these products do, then it is more acidic than their natural biome, right? And so that's why they did that. And so what they found was the diversity of natural skin microbiome increased consistently throughout the study, evident in both the untreated area and after the application of the vitamin C or whatever they used. And they noticed that one of the masks reduced a specific bacterium, which significantly lowered the pH. And that skin pH change corresponds with the microbiota stability. Well, right, if we know that skin there is slightly acidic, right, that 4.5 to 5, 4 to 4.5 to 5.8, then by going back into that range of right around 4.5, it's not surprising that the microbiome improved, right? And so that's just kind of I thought that was really interesting. And if you're interested in that, Google Scholar is a great place to go and see kind of what people are researching. This is a graphic that I got. Ignore this pH range. Again, I found a lot of different ones, but I'm pretty confident in the 4.5 to 5.8 that we're going with. But the reason I wanted to show you this is because we have acne bacteria, and acne bacteria is really happy at a pH of 6 to 7. So that's one of the things we see there. When we talk about vitamin C serums, they do have a much lower pH, right? So they're talking about vitamin C here. That's 2 to 2.5. Stomach acid is right around a pH of 2. Now, this is going to change depending on the formulation that people use. So not every vitamin C serum is going to be this pH, depending on the formulation. So that's something to watch for. You can also see where water, foaming cleanser, and foaming cleanser like soap ends up here. So soap tends to be a little bit more alkaline, and that's what we see. So pH is important. Let's talk about how we measure it. So if you're formulating cosmetic products, you need to measure the pH, right? If somebody's going to put it on the skin, you don't want it to be something that can cause skin irritation. There's a couple different things that we can use. We can use indicators, and one type of indicator is litmus paper, and they change color based on pH, right? So they change color. If you have a pool or have ever done any pool chemistry, the pool kits use an indicator, right, to see if the pools have the right pH. These are different indicators, and one of the things I want you to notice is, so like for example, this is methyl red. It's at a very low pH, it's red. When it gets to about 5, it is kind of this orangey color. And then when we go up here to 10, where we're really basic, it's yellow. So there are different pHs that have kind of different ranges that are helpful for us. This range is right around 5 because, for example, it's really hard to tell the difference between 9 and 10 here. It's really hard to tell the difference between 4 and 2. That's not going to help you differentiate here. So the indicators work in kind of this narrow pH range. So that's why we have lots of indicators. So bromothiamyl blue here kind of works between 5 and 9. Phenolphthalein works between 7 to kind of 10, right? So those are what we have. These are just because you're using the eye as a detector, and the eye is not a great detector, not as specific as pH meters. So pH meters are used for really accurate measurements of pH. You have electrodes, and they can detect really small changes in voltage, and that helps determine the pH. So this is milk of magnesia, which is quite basic. This is the pH probe, and we are looking at the pH there. So we can measure the pH of products. We can also calculate pH. There's several different ways to calculate pH because pH and pOH are related. So for example, because pH plus pOH equals 14, if you know the pH, you can get to the pOH. If you know the pOH, you can get to the pH. If you have the H3O plus concentration of your solution, you can calculate the pH by going negative log and putting in the H3O plus there. If you've got the pH and need to go back to the H3O plus, what you're going to do is you're going to hit the second log button, okay? So whenever you want to do the opposite of a mathematical expression on your calculator, if a lot of times if you hit second and that same button, that's the opposite of it, right? Or anti-log, a lot of times we talk about. What that looks like on my calculator, when I look at the second there, is it looks like a 10 to the x. Now that's not to be confused with scientific notation. So to figure out that H3O plus concentration, you would hit second log and it would be 10, and you need to put in the negative pH, and that will tell you the concentration. You can, if you have the concentration of H3O plus and the concentration of, and you're looking for the concentration of OH minus, you just take 1 times 10 to the 14th and divide to get over here. And then getting to POH and the OH concentration here is really similar to over here. This is just telling us the POH or the hydroxide concentration. This is used somewhat, but it's a little less frequent. Most people stay over here in this pH range. So what I want to spend the rest of the time doing in this screencast are some pH example problems. So we have this problem. It says, what is the pH of a vitamin C serum with a pOH of 11.1? Is it acidic or basic? Well, if I'm giving the pOH, the easiest way to solve this is to use the equation pH plus pOH equals 14. I am trying to get the pH by itself, so I'm just going to take 14 and subtract the pOH. So to get the pH, I'm going to take 14 and subtract the pOH. So that would be 14 minus 11.1, and that would be 2.9, and that would be acidic because the pH is less than 7. Now, this should make sense to us. We know vitamin C is a little bit more acidic, so that's something that we would see there. What's the pH of a lotion that has a hydronium ion concentration of 1.58 times 10 to the 8th molar? One of the things I want to remind you is hydronium can be spelled out like this. It can also be shown like this or like that. So just watch out for those chemical synonyms. I'm asked to calculate the pH. I know the pH equals negative log of the concentration of the hydronium ion. So I take negative log, and I'm going to put 1.58 times 10 to the negative 8th molar and shove that in. And when I do that, I get 7.8, which is basic because the pH is greater than 7. Let's do another example. What's the pOH of a solution that has a hydroxide concentration of 2.6 times 10 to the negative 7th? Well, this is asking me for the pOH, right? And I've got the hydroxide concentration. I know pOH equals negative log of the concentration of the hydroxide ion. So I'll come over here and I'll do negative log of 2.6 times 10 to the negative 7th molar. I will put that into my calculator and get 6.58. And that is, when we look at that, we are not using pOH as a scale for whether something is acidic or basic. So this answers this question, right? If you wanted to find out, right? So if the question said, is it acidic or basic? I think the easiest way to answer that question is get the pH. So to get the pH, we would just take 14 and subtract 6.58, and that would give us 7.42, and so this is a basic solution, right? Slightly basic. All right, what is the pH of a solution that has a hydroxide concentration of 3.4 times 10 to the negative 6? This is a tricky question, and let's talk about why. It's asking for the pH. We know pH is based on H3O+, but it gives you the hydroxide concentration, which is OH-. So to solve this, there's two different ways you can do it. And I'm going to show you the way that I like the best. So the way that I like the best is to calculate the pOH and then solve for the pH, much like we did on the previous slide. So we've got pOH equals negative log of the concentration of 3.4 times 10 to the negative 6 molar. When we put that in our calculator, we get 5.46. So then for the next step, what I'm going to do is I know pH plus pOH equals 14. And so to find the pH, I'm going to take 14 and subtract the pOH. So I've got 14. I'm going to subtract 5.46. My pH here is 8.53. This is a basic solution because that pH is greater than 7. Okay. Now, let's do one last problem. And so we have a company and it states their facial serums have a pH value that ranges between 4 and 6. And so I found a company that gave all the pH values online. They ranged between 4 and 6. And so we're going to calculate the hydronium ion concentration. That's that H3O plus concentration for a pH and a 6 and see what that range is, right? Because a lot of times in our mind, we think, well, that's just 2 pH units. That's not that big a deal, okay? And because this is based on a log scale, it's actually quite large. So let's calculate the H3O plus for the pH of 4.0. When we do this, that H3O plus concentration, right, we would take the anti-log button, the second log, and that's going to be like a lot of times a 10 to the x, and raise it to the negative pH. So that would be 10 raised to the negative 4, and that's got to be the anti-log, right? And so when you do this, you get 1 times 10 to the negative 4 molar, okay? It's important to notice that pH does not have a unit, but the concentration does. That concentration is molarity. Let's look at pH equals 6.0, okay? We've got an H3O plus concentration equals 10 raised to the negative pH. So we'll go 10 raised to the negative 6, right? And that gives us 1 times, I want to take that off, 1 times 10 to the negative 6 molar. Now, I want us to think about these numbers just a little bit. If you go from a pH of 4 to a pH of 6, you have 100 times more acid molecules in the pH of 6, right? So that's a big difference. So pH sometimes can, on the surface, be a little misleading when we have these pH jumps and we're like, oh, well, it's just a pH of 5. How is that different than a pH of 4? Well, that's a 10 times difference. So every pH unit increases the acid concentration 10 times, which a lot of times is called a tenfold. Okay, so pH can really affect the amount of acid that's present. This ends for us our chemical reaction module. As always, we will practice this more in class. And as always, if you have any questions, please feel free to stop by my office.